Hey, K-Team. So I hope this video helps you. And I'm sorry for my English because I think it's going to be a little bit of a long video. And I hope my English is enough so you can understand what I'm trying to, to explain. But all right, so anyways, I have seen that you posted this, and I think there was a similar question like this before. And I don't know. I think that you have to concentrate a little bit more um, into developing a more conceptual framework for the analysis of these things, because all of the analysis that you're asking for in here, domain, series, continuity, singularity, global and local streams, etc., etc. I mean, this is a pretty complicated question because this is basically what you'll learn to do in a calculus course, and this is what you actually learn to do in several calculus courses, and what you are continually studying and stuff like that. It seems to me that you are into math related or maybe engineering related studies or something like that because of the type of things that they are being asked of you. So I would suggest that you become a little bit more abstract in your reasoning, which is why I mean, I hope that this video is going to help to you. It's not going to be a video about doing all of this work for you on this particular exercise, but I'm going to try to give you more like some sort of framework or methodology that you can use for analyzing this kind of stuff time after time after time, because it's always the same kind of analysis. It's just that the functions change, but the methodology is always the same. So for example, for domain, I think I saw another post of you where you didn't have really clear about what was going on about the domain, and I do think that you understand that the domain has to do with all of the allowed values for x, right? So the only thing that you have to worry about when thinking of domain are really very little things. So you only have to worry in the case of whenever you are dividing by zero, right? So this doesn't exist, it's not defined. So that's a problem in the domain. And the other thing that can be a problem is whenever you have a negative square root. So this is also a problem. So those are the only things that you have to really care about the domain. If that doesn't happen, then your domain is all the real numbers, right? So it's like, yeah, every number is valid, because this is the only place, these are the only two places when something happens, right? Now, that analysis could be a little bit tedious or a little bit difficult because, for example, if you have a function that it's being divided, I don't know, let's say by the square root of x minus 3, and up there you can have whatever you want. Then you have to do like a double analysis for your domain, for example. So when is it that x minus 3 is going to be negative? So you have to do the change of subject and stuff like that. And you would say, oh, all right, so whenever x is less than 3, then that doesn't work. So I don't like this point for my domain. But also you have to understand, well, when is it that x minus 3 equals 0? So it's exactly in the number 3. All right, so you have now a very good idea of what is going to be your domain, because it can't be the number 3, and it can't be anything less than 3. So if you are thinking about this in a straight line, then you have number 3, and you can't touch the number 3, and you don't want to be on the left on the number 3. So your domain is going to be everything else, right? So some of these things, and for example, if you had a multiplication inside the square root, then oh my god, because then you have to do like a table and understand which are the places where the signs are going to be negative for the multiplication of these things. So that can be a little bit more tedious, but the same idea applies always. So what is going on whenever you have a division by 0 or a negative square root? And that's the only thing that you have to worry about the domain. So anything that happens after that, then there's no problem. So for example, on this exercise, well, you only have to think, do I have a division by 0? No. And do I have in any of these functions a square root, a negative square root? Could that be a possibility? Well, no, because all of these are only going to be powers. So it's like, oh, all right, so my domain is all the reals, because these are the only places where something bad is going to happen, right? So that's the domain. So it could be it could get a little bit more difficult with different type of functions, but that's basically all you need to know about the domain. So the zeros of the function, I think you also did them in your post. So you just have to equal this to 0 and find the roots, right? So in this case, it's pretty easy, because then you just have to know that if any of these parentheses become 0, then that's a 0 of the function. So y equals -6 or 2 or -2 or +5. All of those are going to be zeros, right? So that's pretty easy. Well, it's pretty easy here, because if you had, for example, a polynomial, and then you have to search for the zeros of a polynomial function, then that's going to be like a nightmare to get it done, and you need different techniques for doing that. But I mean, it's the same idea, right? Now, continuity is going to be a consequence of the domain and the zeros. The only thing that you have to think about continuity is to ask yourself, well, was there, oh my God, I don't know how to conjugate that. Was there a problem with our domain? And if there was no problem with your domain, then to hell with that. It's continuous function. The only thing that is going to tell you if there is a continuity or not is your domain. So if there are places where you can't touch some points on your domain, then there is going to be a discontinuity on there, right? Now, the singularity comes from a similar place from the study of your domain. Once that you have seen your domain, so the singularities can happen, for example, in case of asymptotes. So you just have to think, for example, let's say that you have a function 1 over x minus 3. So whenever you have a function divided by x, it's going to look something like this, or some variation of that. It may have a little bit more turns or things like that, but there are going to be asymptotes on this place. Now, where are going to be those asymptotes? Well, in the places that your domain has problems. So, for example, in this case, if x equals 3, then you have a problem on your domain, right? So everything goes to hell, because you can't divide by 0. And if x equals 3, then this 0, and then game over, right? So what we know is that in this case, however this thing looks, well, I have now a pretty good idea that this is going to be like, there's going to be a displacement on the curve, right? So in x equals 3, so let's say that here is the number 3. Over here, there's a problem. So I'm pretty sure that the graphic of this is going to look something like this, right? And I know that it says do not give graphical reasoning, so just bear with me, because understanding the graphic part of this is usually easier to know than from an algebraic point of view. But it gets easier, right? So if you understand what is going on graphically, then you can transport it to an algebraic expression more easily, or an algebraic reasoning more easily, right? So we were on the singularities, right? And so the singularities, you have to understand what is going on with the graph. So once that you understand what is going on with the graph, then you can say, oh, well, there's a singularity in this example that I'm giving to you, and there is going to be an asymptote, because that's what happens usually when you have a division by 0. I think the other tip that it could help you is that in case that, for example, let's modify a little bit this exercise. So let's put it like x minus 3 times x minus 2. And on the numerator, let's say that because of some reason, you also have an x minus 2. So you still have zeros on the denominator that you have to be careful and you have to be mindful about them. So whenever x equals 3 or x equals 2, there's going to be a zero in the denominator and everything is going to go to hell again. And so there is going to be a singularity or a discontinuity on some of those points. And if I remember correctly, but you should check your calculus book about this, I remember that if there is a factor in the numerator that can be simplified with the denominator, right? So we can just cross this because they are the same. Then that means that this then x equals 2 is not an asymptote, but it's a hole on your graph. So this would mean that there is a discontinuity over there. Discontinuity. And well, so it could be that you have an interesting graph, which I don't know, I would have to graph that. And I mean, I know it says do not give graphical reasoning, but it's just so you can understand like these points. So you could say, all right, so in in plus 3, there's going to be an asymptote. And whatever the thing is doing over here, or maybe it's over there, I don't know. We just had to do the graph and actually see what is going on here with a little bit more detail. What we know is that the asymptote would be on 3, but the discontinuity would be on 2, right? So over here, there would be a little hole. You wouldn't have like an actual value over here. But I'm pretty sure I just read that in a book for a class that I was preparing. But since this wasn't the whole point of the class, I didn't pay like that much attention to it. But if I remember correctly, as I was telling you, if there is a factor that you can simplify with the denominator, then that's a discontinuity. But if there are no factors that you can simplify, then that's an asymptote. And the other thing about asymptotes that you would have to understand or how to analyze them is for horizontal asymptotes. So what is going on if you have a horizontal asymptote, as you would have in any graph that it's of the type 1 over x, right? So whenever you're dividing by x, you're going to be watching this kind of behaviors of the function. So you have to learn how to analyze when x goes to infinity, and then think what is going on with your exercise. So if there is some wonky behavior when x goes to infinity, then you are going to have some sort of horizontal asymptote in some point, right? But you have to like make a deep dive for the analysis of the function. So this is why I was telling you that this is not an easy question to answer, because this is what you actually learn in the whole in all of your studies of calculus. So this is not easy, Katie. This is not easy to try to make a short review in a video. But I hope that these ideas kind of give you a framework of how to analyze these functions, because this is a lot of analysis. So those would be your singularities. Now, what would happen? Well, in this case, there aren't either asymptotes or holes or discontinuities because you don't have any problem with the domain. So whenever you don't have any problem with your domain, then there is no singularity and there is no continuity and there is no nothing, because there aren't any problems with the domain. So this is a little bit more easy, right? Now, what's going on with the global and local extremes? Well, I have always find them like a little bit confusing, or what I don't like about it is you have to know how local are you trying to understand your function, and this is completely dependent on the problem. So for example, sure, if we chop this graph, for example, over here and over here, then this would be not only my global maximum, but a local maximum, because I'm just analyzing like this interval over here. However, if I place like the intervals longer, for example, like this image that you can, I think you can assume that this is going to minus infinity and plus infinity. And so, sure, then this is going to be a local maximum because you also have global maximum. So it has sense to have a local maximum only if you have a global maximum. But there are some cases where the local maximum is also the global maximum if you're seeing, for example, from here to here, right? So the global maximum is also a local maximum. So it depends a lot on the specific places that you need to analyze your graph. So in this particular case, I think this is going to be interesting. So I know there's no graphical reasoning, but I really suggest to you that you make use of the graphical reasoning to understand what is going on, and then the algebraic reasoning is going to be so much easier. So if we were to see the graph, so these are the graphs of the functions that are being given to you. So the red one is the top one, and the blue one is the one on the bottom. So let me just see the intervals to see what is going on here. So the red interval, so this is it, is going to go from minus infinity to 0, but we can actually grab the 0. So this graph, which is the red graph, all right, so I need to take attention of this. So from minus infinity to 0, touching the 0, it means that you would have this graph. And again, I know that it says no graphical reasoning, but it's going to be so much easier this way. And then once that you understand graphically what's going on, then we can just justify it in an algebraic or gridding way, way easier. So your graph is going to look something like the yellow thing that I'm drawing here on the left. And then from 0 to infinity is going to be the other one. So it's going to be the blue one. Oh, all right. So we are going to have a jump from here to here. So there's a discontinuity over there. And I know I said that there weren't discontinuities, but I'm going to make this point clear right now. So it's going over here. So the actual graph of this piecewise function is the yellow parts, right? These are the only parts that are actually defined in our piecewise function. So when I was talking about that there wasn't any discontinuity, I was thinking in the individual on the individual graphs, right? So on the individual functions, I'm sorry. So in this graph, we can actually see that there is a discontinuity because we can touch the 0 value from the left side, but there is going to be a hole when you go to the right side, right? So how do you know these kind of things? Well, if there is an algebraic reasoning and they want you to reason it by algebra, then you would need to make, I think that you would have to make the calculations, and that would be the easiest thing. Like, well, what is going on here? But this is also analysis, and then you would see that, all right, so I can touch the 0 value. So if I substitute 0 in this function, what is going to give to me? And once you do the algebra reasoning, then it has to be this value that is 6. I think it's 6. Let me see. Yeah, it's number 6. So this function is going to give you a value of 6 on the y-axis. And then if you analyze the other point, you can't actually substitute the 0 because it says that you can't touch it. So you're going to have a limit for it, or you can think in the idea of limits. So what is going on very near to the 1, for example, then you're going to see that the value is going to be around minus 10. Now, other ways that you could actually do this, and I don't know if that's going to sit okay with your teacher, is that you would have to know how to, well, no, because I was going to say how to graph them. So yeah, you would have to do all this by hand and make the calculations and say, well, the value of b of y on 0 is going to be 6, but the value of b of y evaluated, so for example, on 0.001 is going to be very near minus 10. So that means that there is a discontinuity, because the point on the second piecewise function is going to minus 10, all right? But the point on the other one is going to 6. So there is no sense that there is a line over here, because you have to remember that those things aren't functions, right? So it has to be a discontinuity because of the definition of functions. You can't have like a vertical value joining this point to the other. Now, you would have to make the calculations, because it could have happened that the second piecewise function, maybe it would start right on the 6, and I don't know, maybe it was a line, for example, over there. And maybe they were telling you that on this place, you can't touch the 0, as in this case, right? So you would have a hole on that line. However, for the piecewise defined function, that wouldn't be a discontinuity, because there would actually be a real value on the number 6. It just means that that value came from the left piecewise function, from the first one, not from the second one. But the final function created by those two, for example, if these were aligned, if this would have been aligned, for example, there would be no discontinuity over there. So you would have to analyze both values over there. But for what I have seen in other of your exercises, I think you already know how to calculate limits. So if they need an grid algebraic reasoning with calculations and stuff like that, well, then what you could do, for example, is to analyze the limit from when x goes to 0 from the left, and then also make the calculation for the limit when x goes to 0 from the right. And if these two limits aren't the same, if they aren't the same, then there is a discontinuity. And then that's the way that you could justify it algebraically in this case, for example. But well, on this case, then you would have to do these limits, and then you would find that there was actually a discontinuity between the two intervals, right? So that would be how is it that you analyze the continuities also. So global and local extreme, as I was saying, that depends on what is going on. So the algebraic reasoning, and we're going to make use of the graph to make it a little bit more easier, is that on the left on your graph, right, from 0 to minus infinity, then you are going to have a global maximum over here, right? Now, how could you do that? Well, you'd have to know a little bit more of parabolas, because on this case, with this expression, y plus 2 times y minus 5, then you could either you can make the product of this and expand the product, and then that function, I'm guessing that you're already studying calculus and know what's going on with the derivatives and the first derivative rule and the second derivative rule. So if you want a more sound algebraic reasoning, then you could derivate, I don't know how to say that in English. You would have to have the derivative of the function of this one, and then analyze what's going on with the rules, so you could find the maximum. But if you have used the graphical reasoning before, then you already know that what you want to justify is that there is a local maximum. I mean, well, it's local for the interval from minus infinity to 0. There is going to be a local maxima over here. And the global, all right, so what about the extremes? Because it says the global and local extremes. Well, the extreme is going to minus infinity, right? How would you know that? Well, because of this minus. So you have to remember what's going on with your wait, no, this is not going to be helpful at all. So the quadratic equation, if you remember your transformation of the functions, and you have y equals x squared. Well, you're already working with functions, so this will be like f of x, it's x squared, and you just have to remember that this graph looks like this with the vertex on the origin. And if you have a minus sign on this place, then this graph is going to be reflected towards the other side. So it's going to be over here. So whenever I see this multiplication, and don't get confused because they use the variable y. I think that's just for confusing purposes. In the end, just changed by x. I mean, still, if you have a function, it doesn't matter if the variable is y. This represents the vertical axis. So whenever I see this minus sign on your function, then that means that the graph is reflected and it's pointing downwards. So when you combine that idea with the idea of your domain, because we already know that for this multiplication, there is not going to be any sort of problems with the domain. So we know that we are going to have a squared function. So whenever you do this thing, I mean, it's going to be y times y, so it's going to be y squared. And on the end, we have this minus, so it's going to be minus y squared. So what I know is that the biggest number is going to come from the y squared. And whenever I place in there, for example, a really big negative number, is going to give me a negative result because of this minus sign. So what I'm trying to say is that here on this graph, it says minus 8. So imagine that this would be minus 8 million, for minus 8,100 billion gazillions trillions over here. Doesn't matter. What is going to happen is that all the values are going to go to minus infinity on the vertical axis, right? And that is going to happen always because of the minus sign that you have over here. So the behavior on the extremes is going to be that it's going to have, it's going to tend to minus infinity on the vertical axis. So you could say that b of y is going to minus infinity on this specific range, from minus infinity to 0, right? All right, so it's going to minus infinity on the extreme, right? So whenever x goes to minus infinity, then your function also goes to minus infinity, right? So that is the way that you would actually have to analyze all of these things. So it would happen something very similar on the other place, on the other function. So the other function is going to be a y squared, a positive y squared. So we know that whenever you place whatever number here is going to go, is going to keep growing. So the bigger the y gets, the bigger the squared y is going to get. For this, again, you need to really understand the graphics and the behavior of different functions, and that's going to be really useful because we usually only study like a little bit more known functions like cubes and quadratic functions and square root functions, for example. So what would happen with a square root, for example? I mean, you would know what would happen if you have a square root over here, even though it seems like it's going to stop. It looks like it's going to stop on some place. It actually doesn't, unless you have an asymptote. So that part of the analysis would have popped up if you had a division between 0 in some place, right? So whenever you had something over something that could be 0, then there would be an asymptote. But in the case, for example, of a square root function, there are no asymptotes. So it looks like it's an asymptote, but it's going to continue to grow. It's just that it's going to be very, 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 very slowly. But on the algebraic reasoning, you could actually argue that, for example, I mean, this would be this would just be the graph of x. You could argue in the algebraic reasoning that since x is going to be more than 0, well, it could be more or less than 0, then this function is going to be defined, which means that it's going to be continuous and that there won't be any kind of singularity, and the extremes are going to behave that they are going to go to the infinite, because this function is going to be continually growing. All right. So all of the behavior of the M behavior and extremes and stuff like that, that is going to come from the analysis of your domain and of the zeros and the continuity on your functions, and that is something that you can do in all of the cases. But I think that you have to think more in a little bit more conceptual terms of what is going on with functions and where are the functions undefined and stuff like that. And then it's just rinse and repeat, right? So you're going to find yourself asking always the same questions. Do I have a square root, and could it be negative, or in which places is going to be negative? Do I have a division of 0, and what is going on? All right, if I have a piecewise function, so what happens if I find the limit from the right and from the left on a point? Are the limits going to match? And if the limits match, then the function is continuous. And if the limits doesn't match or they don't exist, then the limit is not going to be continuous. And what about my singularities? Well, where are the zeros in the denominators? And those are going to tell you about the singularities. And the global and local extremes and stuff like that, then you can actually just analyze the function. So for example, if I were to have this function square root of x, then what would happen the bigger the x that I start to evaluate? And then you could argue that, well, this is just going to keep getting bigger and bigger and bigger. It's just going to be as low growth, but it's going to keep growing unless I have found an asymptote that would be on a previous analysis, right? Now, oh my God, this is a really long video, so I can't talk anymore about the range. So I don't know. I mean, if you find this video helpful, then just let me know in the comment on the group. And if you did find this helpful, then I can make a video to explain the difference between range and image and the things that you have to take care about on the range. But I don't know. I mean, I hope I hope this is helpful to you. If it isn't, then I'm sorry. I'm doing my best with what I know about how I know how to talk in English. But I think the longer that I'm explaining, it's getting a little bit harder to explain it in English. So I need to let my nagging rest. So, well, anyway, good luck, Katie. I hope this helps. And well, I'll read you on the group in case it helps. Good luck.